Hello there. Let's look at intermolecular forces today. We're going to look at inter versus intra. This is actually intramolecular bonds. They are strong bonds inside molecules. So the first example is ionic. The ionic example is sodium chloride. Sodium cations and chloride anions stay together as a crystal, and they are complete trade of electrons, right? And then look at the second one, B, covalent molecules, hydrogen, HCl, and so on. And these ones actually share electrons, and the two nucleus in the each side and the two electrons middle in the middle make a bond, covalent. So these are intra. Then again, another intra bond is metallic. It's called the sea of electrons, and actually the cations, something like aluminum, cations are actually submerged, happily swimming around in this sea of electrons. So that's what the metallic bonding. So all these three, A, B, C, are actually intramolecular, inside a molecule, inside the matter. So that's what this one. So these are stronger, hard to break, and they give completely different properties. Today we're going to look at intermolecular forces. So that's the better term. So where do we have it? In between molecules and atoms. So helium, two atoms in between, and oxygen, two molecules in between. So these are intermolecular forces. Let's get water. I'm going to draw water a little bit differently. See, big oxygen atom and two hydrogens. The hydrogens gets delta plus, small partial charge, and oxygen gets delta minus, small negative charge, right? Now, when they come closer, this delta minus and delta plus interact. That's the intermolecular force. That's actually called hydrogen bonding. So I'm going to go to the details of hydrogen bonding in a moment, but also we can simplify these big water molecules into a simple form like this. And what happens? Hydrogen gets the delta plus, oxygen gets the delta minus, partial positive, partial negative. They interact each other, intermolecular forces, and that's hydrogen bonding. Now these two are actually intra covalent bonds, right? In the white circle. So you have to see the difference. So learn side by side. Now, another way you can memorize and understand hydrogen bonding by this way. See FON, FON, the size matters in this case when they're directly bonded to hydrogens. These are needed intra bonding. You need F2H, O2H, N2H, intra bonding needed. If you do have it, there's delta plus, delta minus. What are the examples? HF, water, methanol, ammonia, methylamine. Those are few examples. So these ones in between going to make hydrogen bonding, just like kind of like that in between molecules. So that's the IMF, intermolecular forces, or attraction. So the bond, hydrogen bond is not the right term, but the old days, we used to use it, right? That's what it is. So now also remember, hydrogen bonding is a dip-dip dipole-dipole type. I call it the VIP dipole. Why? Look at this DNA, and this is alpha helix protein, this is beta sheet proteins. In between these ones there's tons of hydrogen bonding, really important. That's why the life began and thrive. Those are important stuff. If you just flip a biology book, look at it. Now, so we're going to look at few other dipoles. So H2Cl, delta minus, delta plus, these are permanent dipoles, and they will create these intermolecular forces. I call the dip-dip, right? So these are permanent dipoles. HCl, H2S, they have permanent dipole. There's another category simply called ion dipoles, or we can also call it. In the example of ion dipoles, so you just have ions. What are the ions? Cations and anions, sodium plus, chloride minus. So when it is in the water, salt is added to the water, sodium plus is going to attract more with the oxygen delta negatives, and it nicely makes a cage, and we call the solvent cage. And the same thing for the chloride, but the chloride ions are attracted to the delta H, delta plus H, right? So it will be surrounded by hydrogen atoms of the water molecules. So you can understand that, right? Now let's look at induced dipoles. So the induced dipoles are, look at this one, H2S nearby, let's say, hydrogen molecule. Hydrogen is nonpolar, H2 is polar permanently. Now what happens? Because of the delta plus of the sulfur atom, it's going to push the electron cloud of the hydrogen molecule, creating and inducing a delta plus and a delta minus. So those are called the induced dipoles, right? Now, so the next category, the weaker category, the third category, first one was very powerful hydrogen bonding, then the deep, quite still stronger. But London dispersion force, LDF, is transient, very little amount of time. It makes a few picoseconds. And where do you see them? H2, N2, O2, helium, neon, krypton, xenon, all these non-polar species. Now, they are weaker, right? So how do we understand? Helium to helium, they are very symmetric, very nice, but we know the electron cloud is moving around. They're moving really fast. What happens is it's not always very nice pair. It's going to be a little bit twisted, right? So that way it kind of get the pear shape, and then there's a little bit more electron density into one side, just for few picoseconds. Now it makes uh, a temporary dipole, and then they attract each other. So that's how we can get the liquids of all these helium, neon, argon, right? We can get it. Now this one is just to simply show you a long hydrocarbon, not long, 5 carbons, right? And then if you have an open chain, they pack very well. It's called the packing effect, but they're kind of like a odd shapes, like balls and branches a lot. They will not pack well. So that's because of the London dispersion. Okay, so the London dispersion actually have all the nonpolar, and they will become liquid because of that forces, even though it's weaker, right? Now this is my von Clow-Brisch, right? It's a little bit like a German term, von Clow-Brisch. Now the delta minus goes into the delta plus. That's the ranking. But why this is important, you can figure out. Oxygen bonded to nitrogen, who is delta plus delta minus? Chlorine bonded to bromine, who is delta plus delta minus? You can figure this out because electronegativity ranking is kind of given by the size of this one. Now remember the first three, von, when they're directly bonded to hydrogens, they're going to make hydrogen bonding with other molecules intermolecularly. That's the something to memorize in this picture. The other one, any of these members, when they are connected with a different atom, let's say H to the Cl, C to the O, S to the C, Cl to the Br, F to the O, whatever, anything, they will make a dipole-dipole interaction. So they're quite stronger. They can interact, right? Now, if you connect any of the same kind, that means F2, O2, N2, C2, Cl2, Br2, those are nonpolar. Actually, we consider carbon to hydrogen also very close to each other. Okay. Now, today's take home question. So, explain these two graphs if you can. If you cannot, just fire me an email. My folks will give it to me. My people give me, and I will answer that. Right. Okay. So, these are two graphs I gave you. So the molar masses in the x-axis, the y-axis is melting point and boiling points actually, or temperature. Now look at this one. If we draw hydrides of H2O, H2S, H2SC, H2TE, water is actually up there, not in the trend. Now same thing for ammonia. If you get the phosphine pH3, ASH3, and SBH3 and NH3. What happens? NH3 is not in the normal trend downward, but it's way up, right? So this is really important for some of the first year courses, IB, AP, and so on. So try to explain in 2-3 sentences. How do you explain that? Why water is way up? Why ammonia is way up? It's melting and boiling, right? So I think that's come to the end. Thank you.